In this video, we'll introduce the notion of a context window. In the previous video, we've introduced the model of a linear chain conditional random field, which consisted in adding these lateral connections parameterized by matrix V between the computations made at different positions in the sequence that we're modeling. And so this allows us to express some preferences for the assignment of adjacent labels in a sequence. So the goal of doing this is so that the probability assigned at a given position is also influenced by the probability mass that we're assigning at adjacent positions. And so this allows us to model essentially dependencies within the sequence. Another way of doing this could have been to have the inputs, say, on the left of the center position here, K, also influence directly the computation of the pre-activations at position K. And similarly, we could have had the input at the position on the right at K plus 1 also be used directly in computing the pre-activations at the output layer for position K. So we'll see two different ways of doing this in the conditional random field. All right, so generally we'll talk about a context window referring to the set of inputs that will influence our prediction, so our preference about the value of a given label at a given position. So context window is going to include all of the inputs at a given position that influence the preference that we are assigning to to different labels. So more specifically, currently in the linear chain CRF, we have that the P of y given x is the exponential of a set of terms that depend, that involve each label yk for different positions k, and that involve the current input at the same position xk plus our pairwise term. Now, if we consider a simple example where we have a context window of radius 1, what this would mean is that we would also add two other terms, a set of terms, or a set of terms, a first set of terms which will essentially influence how the input on the left of a position k, how it influences how likely we think yk is. So we're essentially going to have a neural network for a position that will take the input that's always on the left of the current position k, so that's xk minus 1, and that will compute a pre-activation output which will assign for each value of yk a particular preference, whether this neural net thinks that how likely does this neural net think that different values of yk are to be observed. And similarly, we can have another neural network, but for the position on the right. So it's going to tell us how we think yk is likely given the input on the right of the position k in the sequence. And so it's going to take xk plus 1, and then this neural network is going to compute a pre-activation vector from which we'll be able to consult how this neural net thinks based on what's on the right, that the value of yk, whether the value of yk is likely or not. And notice that I've changed slightly the notation here. I've added here 0, here minus 1, and here plus 1, just to highlight the fact that essentially these three pre-activation vectors are computed by three different neural networks. So there's one neural network centered exactly on the value k, one that looks at the relative position on the left, so relative position minus 1, and another one relative position plus 1. Okay, so these are really three different neural networks that take a different input at a different relative position with respect to a current position k. Okay, so this is one way of having the probability for a label at a given position to be dependent now directly on the input that is not at the position k, but at is in this case at the position k minus 1 or the position k plus 1. So again, if we look at the flow graph for computations, then it essentially means we're adding a set of connections that go from the input on the left and then go eventually on the pre-activation vector at the position on relatively on its right, so at position k. And similarly, we have another set of connections which are different, so it's a different neural net that goes from xk plus 1 and then influences the pre-activation that determines the that influences the probability of yk. Another perhaps simpler alternative would be to use a single neural network but feed it the whole context window, that is the concatenation of all the input vectors that belong to the context window at a given position. And so this will allow the neural network to learn about the whole context jointly, the relationship of the whole context with respect to the labels at the different positions. And so in this case, the notation is much simpler. So we have a single neural network. We don't have a comma 0 here. But its input is computed based on the both xk, as we had before, but also xk minus 1 and xk plus 1. So one way of doing this is just concatenate these three vectors and feed that to set that as the input layer of the neural network, and then perform forward propagation until we reach the last hidden layer. So of course, in this case, we'd have more parameters for the first hidden layers because we'd have to connect also xk minus 1 and xk plus 1 to the hidden layer. But the other hidden layers computation would not really change. It's just the first hidden layer that would now depend on the whole context window. And as before, we have our linear chain parameters here, which influence how much we like seeing adjacent values of the label in our sequence for which we're computing a probability. And now because this sum runs from 1 to k, and because xk minus 1 at k equals 1 is x0, and that does not exist in our sequence, and the same thing for at k equals capital K, then capital X capital K plus 1 does not exist as well. Well, arbitrarily you can just choose to set those vectors to 0, or we could choose some special vector that would essentially inform the neural network that it's on either edge of the sequence, if we think that's practical information, useful information for influencing the probability of the symbol on the borders of the sequence. So now our linear chain conditional random field would look like this. So now the input at position k would be the concatenation of xk minus 1 and xk plus 1. And so now it would have all these pixels and these pixels and these pixels as input, and then it would propagate until we reach the pre-activation output layer. So the output layer and compute the pre-activation there to get our term in the conditional random field. And so similarly, for instance, this character would be on the right here and it would be on the left of the context here. So the same character will actually be present at different positions in the input of the here 3 neural networks. Now we'll introduce a different notation, which is simpler and will so simplify the math for the rest of the videos. So first we'll introduce the notion of a unary log factor. So we'll see more why we call these log factor, but they're unary because they are the terms that only depend on a single y at a single position k. So for instance, if we look at the case where we had 3 different neural networks, one that looked at the center, another one on its left, another one on its right, well, all of these terms here, they each depend only, their expression on each depends only on yk. So essentially, these are the terms that express a preference for the value of y at the position k only. that is based on it's a preference only on yk, not on a pair of values of for y's. And similarly, for the case where we have just a single neural net with a context window as input, well, in this case, it's only the term pre-activation term that looks at the whole context window. This term only depends on the single y value at the specific position k. Okay, so for both of those, I'll just use the notation AUYK. U is for unary because it depends on only one label, and YK to specify for which variable are we computing the unary factor. And notice here that the k here also specifies the position. So yk is a variable, but also we'll use, just to simplify again the notation, we use the value of k here to inform us that this term is computed based on the position k. And so these will be the unary log factors. And we also have pairwise log factors. And they're pairwise because they involve a pair of labels, adjacent labels. And so we have AP for pairwise. And then in this case, it's only the term that looks at the entry yk plus 1 in the matrix V. It's the only pairwise log factor. And so quickly, the reason why we call them log factor is because here, so if you write down P of y given x with this new notation, we get the exponential of the sum of the unary log factors plus the sum of the pairwise log factors, where we iterate over all possible positions. And the reason why they're log factors is that we could write this as the because the exponential of a sum is the product of exponentials, we could write this back as a product of some exponentials of unary log factors and pairwise log factors. And so the exponential of a log would just be a factor. And so for this reason, because they appear because they are exponentiated in this expression here, we say that they, instead of being factors that are being multiplied together, they are log factors which are being exponentiated and then multiplied together. Okay, so we'll continue using this notation, and just know that, well, for the pairwise factor, we always use this for the next videos. And for the unary factors, well, we could either use this case here, or we could use a single neural net with a big context window.